So you have nucleophiles. We discussed nucleophiles today. Nucleophiles are electron-rich species, and this electron richness is due to the presence of lone pair of electrons or pi bond. Now the examples of nucleophiles, you can consider OH minus, CN minus, then I minus. This is I minus. I'll just cancel this here. Iodide ion and OCH3 minus methoxide ion, methoxide. Br minus bromide ion, Cl minus. Now these are strong negative nucleophiles, negatively charged. They are considered to be negatively charged. Nucleophiles are considered to be strong nucleophiles. Now we have neutral nucleophiles. The examples are water molecule, NH3. Remember, they are bases. They are Lewis bases. They are actually Lewis bases, which are ready to donate electrons. NR2. NR2H, RNH2, all these are neutral nucleophiles. So we consider them as weak nucleophiles. Now, whenever you think of OH minus, Cn minus, I minus, which reagents will give you these compounds? Which are the reagents? Which are the reagents that gives you sodium OH minus? Say suppose it's something like you want to do a reaction with OH minus as nucleophile. What simply you have to do is take sodium hydroxide. Take sodium hydroxide, and normally you dissolve this in water. So what you end up with Na plus and OH minus. So that is how you generate. In the case of cyanide Cn minus, suppose you want to do a reaction using Cn minus, what you have to do is take sodium cyanide or potassium cyanide and dissolve in water. I minus also you can do the same way, sodium iodide, but OCH3 minus you can generate from sodium methoxide. It is generated from sodium methoxide, which is available in the market. You can get it ready-made, but it can be prepared by adding sodium into methanol. You can see this reaction. Sodium into methanol. Methanol is CH3OH. So this gives you CH3ONA plus H2. Hydrogen gas will be evolved when you are adding sodium. It is very similar to the reaction of sodium with water. Na plus H2O. See here. The product is, you will never, most of you will write NaOH plus H plus. Don't do that mistake. NaOH plus. Many of you will have a tendency to write H plus. Don't write that, it's wrong. Because a base and acid cannot go together. So this is an acid, this is a base. So they will not go together. This is OH, sorry, H2O, not H2O, it's hydrogen gas. So that is how you prepare the sodium methoxide in the laboratory. Similarly, sodium bromide, sodium chloride. Now, in these strong nucleophiles also, you have a gradation of strength of nucleophile. One of the strongest nucleophile is I minus. You can see I minus is a very strong nucleophile. Can anybody tell me the reason for that? I minus is a very strong nucleophile. Why? What should be the reason? Can you think? Compare the different nucleophiles here, like I minus, Cl minus, and Br minus. Now, what is a nucleophile? Nucleophile is something which is ready to donate electrons. Ready to donate electrons. That means it should possess it's having excess of electrons. So the more more the electronic charge, more electrons are available in the valence shell. More electrons available in the valence shell, more it is ready to share. More ready to share. Right? Now look at the valence shell. Look at the valence shell. In the case of see the valence shell. In the case of iodine, you have iodine. If you look at the periodic table, it is the order of halogens. You have fluorine. I'll write it here. That looks a bit better. So if I take the periodic table, the 70th group, if I take, I'll have my fluorine on the top, then chlorine, then bromine, then iodine. That means the number of shell, this is a number of period, second period, third, fourth, and fifth. See that. That means you have in the central nucleus iodine, a very heavy nucleus, and you have one shell, second shell, third shell, fourth shell, and fifth one. So you have I minus 8 electrons in the outmost orbital of fifth shell. Now you compare this with the fluorine 1 and 2. So this is what it works out. So you have 8 electrons in the outermost of fluorine, which is very close to the nucleus, so strongly attracted. But you have so much of shielding effect. The electrons here will be shielding these electrons. So the net charge experienced by the nucleus to the center is very weak. So this is very readily it can form bond with other compounds. Okay. So this I minus is one of the strongest nucleophiles. Then Cn minus is also a strong nucleophile. OH minus is also very relatively stronger. But compared to this, you have Br minus and Cl minus, which are weak nucleophiles. Okay. Now let us look at a few examples. Work out a few examples, identifying the nucleophiles and the electrophiles. Let me write a few reactions, which you can try by yourself to see which are nucleophiles, which are electrophiles. Okay, I'll write a few reactions here. H plus and H minus. You can write complete equations and identify the electrophiles and nucleophiles. So I'll write a complete the reaction and identify nucleophiles and electrophiles. So that is what you have to do. So there is one. Then you have SB H plus OH minus. Then C, very simple ones. Yeah, CH3 plus and CH3 minus. Suppose they are reacting with each other. Remember, whenever you have a negative, you will have a lone pair of electron. So when they combine, what do you get? When you have CH3 plus and NH3. What do you get? So these, okay. So this is these are the, you can identify the. I'll take the first example. Here you have the one which is having, this is nucleophile. Very evidently it's nucleophile. Electron, this is electron rich. It's electron deficient, and this you call as proton. This you call as hydride ion. Hydride ion. H minus. Now see how they react. See, you will get an experience of writing the arrow. See here, this lone pair of electron attack this H plus. Remember, you are always starting the arrow from the electrons, from a pair of electron, and your product is H2. It forms a gas. H2 gas is evolved here. So similarly, you can complete all this writing the arrows. Okay. So these are the nucleophiles and electrophiles. Now let us look at the next area where we have to. Now let's see what I'll go strictly by your syllabus. That is that looks very, so that you can be, I mean, you don't feel being distracted. Yeah. So that is, now let's look at the next area is reaction intermediates, carbocations, carbanions, and free radicals. Okay, the types of this, and then their hybridization, their stability. We'll discuss all of them. How are they being formed? Okay, so carbocations, carbanions, and free radicals. Carbocations, carbanions, and free radicals. Okay, we'll see carbocations. First of all, you can see carbocations. They are positively, a species containing positively charged carbon atom. Species with positively charged carbon atoms. Carbon. Examples are CH3 plus, then CH3, CH2 plus. You can see here, these you can call as primary carbocations. Then you can have secondary carbocations, CH3, H plus isopropyl carbocation. This is ethyl carbocation, methyl carbocation, isopropyl carbocation, and here is tertiary butyl carbocation, CH3, CH3. This is tertiary butyl carbocation. Now you have to compare this. How do you classify this? Look here. You have now C, H, H, and H. You can see only one carbon is there. No other carbon is there. Similarly, here also you have. So this is uniquely we say it's methyl. Now here you can see the ethyl is having one CC bond. All others are hydrogen. So this carbon, this is connected to only one carbon. Connected to one carbon. Such a carbon where you have only connection with only one carbon is called primary carbon. So this is a primary carbocation. A primary carbocation. Primary carbocation. Now here I have got C here, CH3 here, one H is there, and another CH3. So you have two carbon-carbon bonds connected to two carbon atoms. That is what is called what you call as secondary carbocation. And then you have three of them, which you call as, so three carbons are attached, and you call this as tertiary carbocation. This primary, secondary, and tertiary we are going to come across quite often in our discussions. So don't forget the definition, that is quite important. And don't look for the number of hydrogen, but look for the number of carbon atoms to which they are attached to decide whether a carbon is primary, secondary, or tertiary. And now let me directly give you the stability point. From stability point of view, this is more stable. Tertiary carbocation is more stable than secondary, than primary, than methyl. So this is the order of stability. Order of stability is primary, secondary, and tertiary. Primary, methyl, less stable than ethyl, less stable than isopropyl, which in turn is less stable than T-butyl. Okay, so see, stability means once it is formed, it should be stabilized by resonance or by the delocalization of charge. Okay, so that is the condition of stability. More delocalizable delocalizable positive charge. More delocalizable positive charge, more stable. So that is the criteria. If you are able to delocalize the charge, that species is going to be more stable. So that is a criteria. So this is carbocation. Let's see how the carbocations are getting generally formed. Say for example, I got a CH3 Cl. This can undergo a heterolytic bond fission to give you CH3 plus Cl minus. But remember, this is not easily formed. Not easily formed. Not easily formed. Why? What is the reason? The CH3 is not stable. But you can see if you are taking tertiary T-butyl chloride, Cl, you are taking T-butyl chloride. Now this can very easily dissociate into CH3, CH3, and CH3 with a positive charge. Okay. So in the earlier classes, we have seen how to draw the three-dimensional structure of each of this species. You can see that there are three bonds, three hybridized sigma bonds between carbon and carbon. Okay, and you can try if you this is all these three bonds are drawn in the plane of the paper or plane of the board, and you have an empty orbital which is perpendicular plane. So you can denote this as like this. So this is the empty orbital, p orbital. This empty p orbital is a perpendicular plane to the board. Now, if you rotate this, if you rotate along this axis, -90-degree clockwise, just rotate it by 90 degree, either clockwise or anti-clockwise, makes no difference. You will get, if you are rotating clockwise, this will come to the front, goes to the front. This will go behind. And this will remains as such. So you are rotating along this axis, vertical axis. That's why this will remain as such. And you can draw the figure something like this. See here. This bond comes to the front. So one of the CH3 will be here. Second CH3 will be here. And the third one will be here. What about the p orbital? The p orbital gets rotated. It gets projected from here and here. Okay. Otherwise, you can draw this in this fashion. Just rotate in the plane of the board. You can write this in this fashion also, where the CH3 rotating in the plane of the paper. Just rotating in the plane of the paper. See here, all the three CH3 groups with the empty p orbital. So if you have a carbocation like this, and then if you are attacking a nucleophile, If you are attacking a nucleophile, remember this nucleophile can approach either from this side or it can approach from the bottom side. So if it is approaching from the top side, this will bend downwards slightly. All these three will bend slightly downwards to form a tetrahedral carbon. If it is attacking from this side, they will bend to the opposite side, so that the actual bond angle of 109 is achieved. So this is a carbocation stability and its geometry. Don't forget the geometry, that is quite important, especially when you have to discuss the when you have to discuss the stereochemistry of the products obtained. Now, so that is stability and geometry. Then hybridization, you know, it is sp2 hybridized. sp2 hybridized. We have studied hybridization before, I don't want to discuss that in detail again. Hybridized. Let us look at carbanion. Okay. You can see another carbocation being formed, another example of a carbocation being formed from a double bonded compound. This we have seen sometimes before. You can form a carbocation here. It is stabilized by the presence of NO2 group. Okay. So this is also, you can see, this is stabilized by the carbocation generated due to the presence of NO2 here. Similarly, you can have a carbocation like this. You have a double bond, SC. Suppose you react this with what? H plus. I can give you a carbocation, two types of carbocation. See here, O minus and plus. And also this can, see this bond shifts here to delocalize this positive charge, and that will give you another carbocation. See here. So this is quite stable. O minus and a positive. So this carbocation is a more stable tertiary carbocation. So these are the ways by which you can generate the carbocations. Okay. Now we'll take carbanions. Carbanions are a carbon with a pair of electrons, which can be CH3 minus, C2H5 minus. Okay, so carbon bearing a pair of electrons. Now again, the order of stability, CH3 minus is more stable than, it's in the reverse of carbocations. CH2, CH3 minus, still more stable than CH, isopropyl carbanion. which is still more stable than tertiary butyl. You should write the lone pair of electrons that you should not forget. CH3 okay. So this has to be stabilized. That is what you have to remember. If you have some electron withdrawing group, they can be very easily stabilized. Say for example, so that is why this is highly stable. This is comparatively stabilized. This is least stabilized because of the concentration of electronic charge. There is no delocalization of charge. Okay. So this is the order of stability. The geometry is roughly tetrahedral. You have a hybrid orbital with 2 electrons carrying negative charge. Then we have, see the structure of a methyl carbanion. So this is methyl carbanion. The 4 bonds are sp3 hybridized. The sp3 hybridized carbanion. So you can consider this roughly tetrahedral in nature. Tetrahedral. Nearly tetrahedral. And also you can say this is it can undergo a reverse. You can write this in this way also. There's an equilibrium. This can undergo okay. You can write this on the either side. Okay, so that means in the intermediate stage, you will have almost a this is going up and down, up and down. So intermediate stage will be almost like that of a carbocation. So here also they can act as nucleophiles. Carbanions can act as nucleophiles because they have got they are electron rich. Okay. Now generation of carbanions. Methods of synthesizing or forming carbanions. One of the best methods is formation by organometallic reagents. Most common method is preparation of carbanion by organometallic reagents. For example, you must have heard the word Grignard reagent. Grignard reagent. That will generally form carbanion. What is Grignard reagent? You take an alkyl halide. Here is the alkyl halide. React with magnesium. What is an alkyl halide? Let me write CH3. Cl, a simple alkyl halide. It is reacted with magnesium. See, this organometallic reaction is an insertion reaction. You are inserting a metal in between. Right? Invariably, you see this process. Mg and Cl and MgCl. So this is what is called Grignard reagent. Grignard reagent. Okay. So how do people do it? This has to be an anhydrous reaction. This is generally done in solvent like ether or THF. tetrahydrofuran. These two are the solvents which are used. Remember, ether is a solvent. You must be knowing the structure of ether. Don't forget that. This is the structure of ether. It is inert. It will not react with this reagent or the product. Okay. So this is ether. And THF is tetrahydrofuran. See the solvent. 2 down pairs. So tetrahydrofuran. Tetrahydrofuran. Okay. Tetrahydrofuran. Now this is diethyl ether. Diethyl ether, and this is tetrahydrofuran. You prepare this, and this see here, we have studied the concept of bond fission, heterotic bond fission. You can just think about here. Think here. This CH3 Mg bond. Mg is the metal. This is in second group. Mg belongs to second group. Carbon belongs to fourth group. Carbon belongs to fourth group. So, which is more electropositive and which is more electronegative? So, magnesium being in the second group is more electropositive. So, magnesium is electropositive and carbon is more electronegative compared to magnesium. Okay, so you see here, in the case of CH3, I will write on the other side. That is better. For you to have a better understanding, CH3, Mg, Cl. Here, suppose this bond is highly polarized. This is delta positive. This is delta negative. That's what we have mentioned here, electropositive and electronegative. Now, if this bond breaks, the bond, heterotic bond fission, don't forget, it breaks only in this side. And that generates CH3 minus plus NaCl plus. You have to remember, these are not readily available. These are only intermediates, carbanions, intermediates. This will occur only in a reaction mixture. It will not, you cannot get under. You can go to the market and get a little 100 ml of carbanion, methyl carbanion. Not possible, but this is available. Retinol reagents are available in the market, even though they are very unstable. You can get the chemical suppliers will supply you, but not the carbanions. So when you add into this some reagent which will react like ketones, this will be generated and that immediately will react. So that is similarly, a second method is formation from lithium reagents. Or metallic, organometallic lithium compounds. See, for example, N-butyl lithium. N-butyl lithium, you can see it is NBU minus and Li plus, which is generally prepared from, say, lithium bromide. No, lithium reacted with butyl bromide, NBuBr. Okay, two atoms of lithium will react with N-butyl bromide to give you NBuLi plus lithium bromide. So this is one of the disadvantages. Half of the lithium is lost as lithium bromide, but it's okay. That is what we. So this is carbanion. Then you have other organic metallic reagents like copper, which also will generate the negative species. To break this copper organometallic compounds. Organometallic compounds with copper, cadmium, organometallics with copper, cadmium, all these will generate carbanions. Another carbanion is, you can see any carbanion generated like this, NO2 plus. Carbanion which is very close to a electron withdrawing group. They are considered a stable carbanion. See here, this is if you have a NO2 group attached or a CN group attached. A CN group attached here. The carbanion is this type. Why? Because these are stable, because they can be stabilized by resonance using the CN and NO2 group. Okay, so these are stabilized carbocations. This also is stabilized one, considerably stabilized carbanion. See here, alpha carbanions which are alpha ketone. See here, more stabilized carbanion. The carbanion is still more stabilized because these electron pair, you have electron pair here, 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 and here. Everywhere you have electron pair. This electron pair, this negative charge can be delocalized over to the oxygen, these two oxygen, which we will discuss during when we talk about resonance structures. While writing the art of writing resonance structures, we'll discuss all those stability point of view. So these are the different carbanions, different carbanions which are stabilized. Okay, now let us look at free radicals. Something in between carbanion and carbonium ion, the carbocation. See, carbocation, you have an empty orbital. Carbanion, you have an orbital with 2 electrons. So this is carbocation. And this is carbanion. A free radical has got 1 orbital with 1 electron. And this is negatively charged, this is positively charged, this is negatively charged, and this is neutral. Charge is 0. So free radicals are neutral species. They are just directly atoms. Okay, and they also have almost this intermediate geometry between the sp2 and sp3 hybridized. You can consider that way. This is the, you can consider them to be nearly sp2 or sp3. You must be knowing the reason. If you compare this carbanion and carbocation, you can see it will be nearly this type. With what odd electron, or you can consider them to be almost this way, with one electron flowing from the top to the bottom. So it's almost regular geometry. And free radicals are generated from homolytic bound fission formed from homolytic bond fission. Homolytic bond fission, which we have discussed before. You must be remembering that. Now here is a Cl, single bond Cl. Okay, and in presence of light, this undergo bond fission. Here is one electron. Here is a second electron. And you get 2 Cl dot. This we have studied before. Okay. So similarly, you can have other free radicals. Now you can generate a free radical. See, you have H2O2 peroxides, hydrogen peroxide. This can undergo a very good source of free radical, OH dot. Okay. Benzoyl peroxide. Benzoyl peroxide. That also can undergo free radical breakup. So this is a very quite stable one. Oh. Okay. So benzoyl peroxide. So these are the free radicals which are formed from homolytic bond fission. So these are the general reaction intermediates: carbocation, carbanion, and free radical. We'll come across different reactions involving them. We'll go into more details of these things maybe when we start discussing about reaction chemistry. Okay, so we'll stop here and we'll continue next year. Thank you.